Okay, so this video is part 2 of characteristics of exponential functions. This is the back of the notes we were just working on. So on the back, it says, given the exponential function, list all key features, hint, create a sketch of the graph. So on the front side, we dealt with these two graphs, and neither of them actually had the function. It was just the graph. On this back side, we're just given the function and no graph. So a couple things that we're going to talk about for the next couple days. The base of the graph of the function is the part that's attached to the exponent. So right here, so that whole thing is the exponent with the exponent. So your base is the 2/3. So 2/3 is the base, and then you have to figure out if it's growth or decay. So 2/3, if you put that into your calculator, handy dandy calculator, 2 divided by 3, you get 0.666666666. So this is approximately 0.6, we'll just say 67. 0, because it's 0.6, this is going to be decay. And we'll talk about this more in notes later on. But it's decay because your base was less than 1. If it's greater than 1, then it's going to be growth. And be very careful because sometimes it's not just a fraction. Sometimes you can have a base that's like 3/2 to the x. So 3/2, though, if you make that into a decimal, that's 1.5. So this right here would actually be growth. So it's not only because it's a fraction, but you have to make sure it's bigger than or smaller than 1. Okay, next we're going to look at the domain. So the domain, we said, for all exponential functions, and it's exponential because there's an x in the exponent. So the domain is negative infinity to positive infinity. Then from here, I'm going to now sketch the graph because I can't answer anything else really easily without sketching the graph. So I know I have an asymptote. There's a dashed line for all exponential functions. This dashed line, this asymptote that I just drew right here, is actually going to be up here at 5. It's always the number at the end. And remember, it's horizontal, so that's going to be y equals 5 for my asymptote. Then I have to draw my banana-shaped graph. So I either have to draw it increasing or decreasing. Well, we already said it's decay because of the base, so my graph is going to look something like that. So based off of this graph, I can figure out the range. Remember, your range goes from bottom to top. And again, this has a bottom. The asymptote is your bottom. It's your floor. So 5 to infinity. And with all of these, you get parentheses. You cannot touch the asymptote, and you can't ever get to infinity. Okay, I'm going to skip the y-intercept for a second. Think about the x-intercept. So when I am looking at this graph, I moved the whole graph up 5. So I had a graph that was on the x-axis, and then I moved it up 5. Oh, and I'm drawing it the wrong way, but I moved it up 5. So because I moved it up 5, your x-axis is all the way down here. So this will actually never cross the x-axis, so you can just write none. For your y-intercept, your y-intercept, we're going to use our calculators, and because it's the y-intercept, x comma y, the y is going to be the number, which means the x has to be 0. Just like if I had an x-intercept, the x is the number and the y would be 0 if I needed it. So on here, I'm going to go ahead and scoot down a little bit. Let me rewrite our function. So this is the function we're working with. I'm going to use this and plug 0 in for the x. So in my calculator on my screen, I'm putting 0 up here. So let's go ahead and type that in. So turn it on, clear it out. We're just on the home screen. So I'm doing 2 parenthesis fraction 2 divided by 3, arrow to the right, close parenthesis. And then this x minus 3 is up top. So you're using this caret button right here. And it's not x minus 3 though. We said we're plugging in 0. So 0 minus 3. And then this plus 5 is big, but I'm still up top. So if I arrow to the right, or, yep, you have to arrow to the right. Then you go plus 5, enter. And you get 47 divided by 4. So 0, 47 divided by 4. Now, if I was actually graphing this, not just had a sketch, but actually wanted you to put it on graph paper, 47 divided by 4, honestly, I have no idea what that number is because it's a fraction. So if we were graphing it, make sure you press the little double arrow button and it'll give it to you as a decimal. So 11.75 is the number we'd actually graph. Okay, then we have interval of increase and decrease. So let me go back up to my little graph. Remember, you're only going to have one or the other. We already said it was decay, and we already drew our function. So it's going down, it's decaying, so we're using interval of decrease. Remember, it's going to decrease the whole time, which means increase, you have to write none. Don't leave it blank, make sure you write none. Finally, we have our end behavior, and even though we don't have a graph, we can still find it. That's why we sketched it. So as x approaches negative infinity, that's as I go to the left side, on this, my graph, this is the left side, is going up. So it's increasing. So I already figured out that the left side's increase, which means the right side should be the asymptote. So I'm looking at the right side, and yep, it's right there on the asymptote, right where I labeled it. So 5. We're not going to do the average rate of change for this problem, but just know, just like we did on the front, even if it's labeled at interval notation like this problem means I have 0 as an x and 2 as an x, and I'm trying to find the y values. This is the same thing. This is not a point. This is x1, x2. So that means I have -1 as a point, 2 as a point, and I have to find the other piece to it in order to find the average rate of change.